Good morning. Welcome to this next lecture on complex variables. We have been seeing a few examples involving contour integration, and we even saw one example that involved a branch cut. So this next example will involve a finite branch cut, and the integral we are interested in looks like this: integral -1 to 1 square root of 1 minus x square by 1 plus x square dx. Let me mention one more thing. There is another good book on complex variables. It's Complex Variables Introduction and Applications by Ablowitz and Focus, two authors. Some of the examples, in fact, I have taken from this book, as this particular one. Now, as usual, we are going to evaluate this real line integral using principles of complex variables. So, as I have said before, I will introduce a integral on a closed contour C and replace x with z, but make some slight change. So, I will make the numerator z square minus 1 dz by 1 plus z square. So, you will see why that small change has been done. Now, for one thing, this integrand has isolated poles at z equal to plus minus I. Okay. And the contour I am going to choose is this. Maybe I will put it in the center. The contour I am going to choose is this. So, I have 1 here minus 1 here. I come from above. So, let me put my poles. One pole is here, the other pole is here. So, I come from above, take a detour, go off to infinity. At infinity, I take a left, go around. This is a circle with radius infinity. Okay. I come back up here. Okay. I almost join up, and I will join up. I come down, take a detour, go around this at an epsilon circle, come down below, go around here in an epsilon circle and join up. So, the directions are these. Here I come down, okay. So, this is a closed contour. If you see, this is a closed contour, that encloses this pole and this pole, and that's the only that's one of the regions where the function is singular. Okay, and there is going to be a cut over here, a finite branch cut over here, as discussed last time. So let us see the definitions of z minus 1 and z plus 1, because we have a square root here. This involves a square root function. Okay. So let me write here perhaps, let me write here. So let us say z square minus 1 square root is given by square root of z plus 1 and square root of z minus 1, and z minus 1 I replace with magnitude of z minus 1 and e to the power of I theta, okay, which is I will write as rho 1 e to the power of I theta, and theta definition is twice pi. Similarly, z plus 1 is magnitude of z plus 1 e to the power of I phi, and I write this magnitude, it is a positive number, rho 2 I phi, and phi definition is also twice pi. Now we have seen last time that with this kind of a definition, the branch cut is going to be between plus z0 and minus z0, in this case plus 1 and minus 1. Okay, that is the branch cut which we are not allowed to cross. Now the square roots now, okay, so what happens is square root of z plus 1 times z minus 1 are given by rho 1 rho 2 to the power half and e to the power of I theta plus phi by 2. Now let us see this function, what form it acquires in various portions of the complex plane as we move along the contour. Okay. So we have a region here greater than 1, we also have a region we have to think of less than minus 1, we will be moving just above the cut, we will be moving just below the cut. So what is the form this function is going to take? So let us see, z square minus 1 to the power half is equal to, okay, first let us think of 1 less than x less than infinity. So on the real axis here, on the real axis here. Okay. Now if I draw my phasors, this is a point z, this is z minus 1, this is z plus 1. Okay. This is z. So here if I look at square root of z minus 1, then theta here is 0, phi here is also equal to 0. So I get rho 1 rho 2 to the power half e to the power of I 0 plus 0 by 2, which is a positive real number rho 1 rho 2 to the power half. So, all over here I have a positive real number rho 1 rho 2 to the power half, and therefore, this function will look like x square minus 1. To the power half. Okay. What about minus infinity less than x less than minus 1? What about here? What about in this range? Here again I have square root of z square minus 1 given by rho 1 rho 2 to the power half, but here theta is equal to pi, phi is also equal to pi. So, I get e to the power I pi plus pi by 2, and therefore minus a real positive number. Okay. So, that would be x square minus 1 to the power of half, the minus. So, now what about the where we have minus 1 less than x less than 1, just above the x axis y is equal to 0 plus. Okay. Here rho 1 and rho 2 still positive real numbers, but right here we have seen last time theta is equal to pi, phi is equal to 0, and so I get e to the power of I pi plus 0 by 2, and therefore rho 1 rho 2 to the power half, a positive real number into I. So, it will look like I times square root of 1 minus x squared. Okay. Then for the same part below the x axis, minus 1 less than x less than 1, y equal to 0 minus, we have again rho 1 rho 2 to the power half, but below my theta is still pi, but phi is equal to twice pi. Okay. So, phi has to go a full round and come back here 2 pi. So, I get e to the power of I pi plus 2 pi by 2, which gives me minus I, a positive real number. So, here it will be minus I square root of 1 minus x square, because x is less than 1. Okay. Now, let us see how many portions or how many legs we have in doing this integral. I have j given by this closed contour c and the function which is equal to, let us say, the integral in the upper portion, we will call it 1 here as we move just above the x axis, plus this I call C epsilon 1 and this I call C epsilon 2. So, I have then integral C epsilon 1, which I will call it number 2. Then I have integral going below the x axis. So I will call that lower portion. Then I have integral C epsilon 2, which I have written there, C epsilon 2. Then I have these vertical portions going up and going down. I will write them together, going up L1 plus L2, coming down L2. So these are L1, L2. And then lastly, this integral on a counterclockwise circle with radius infinity, I will call it CR. So plus integral CR, okay, that will be equal to twice pi I times the residue at plus n minus I. Okay. So now right away let me tell you that the function is not well behaved or not analytic at these isolated singularities plus minus I and around the branch cut. Branch cut is where the function does not have unique values, so it is also a singularity. Otherwise the function is analytic and well behaved everywhere. So now if in such a region I have an integral goes up and comes down, and these L1, L2 are very close or finally overlapping, then one going up and one going down, they will cancel out. So I will set them to 0. Together they are 0. So we do not deal with them. Okay. Now we have to deal with 1, 2, 3, C epsilon 2 we will call it 4 and CR we will call it 5. We have to deal with 5 portions. So let us look at C epsilon 1 and C epsilon 2 in one shot. The C epsilon I in general, C epsilon I integral in general, okay, I will write it as C epsilon I z square minus 1 to the power half by 1 plus z square dz. Okay. Now again we do the same argument, magnitude of this integral, okay, is less than or equal to the integral 0 to 2 pi of the magnitude. So we have on top the magnitude of square root of z minus 1 and the square root of z plus 1 divided by, okay, here also we have dz divided by, now let me just show it here. Let us say we are doing C epsilon 1. So I am here at 1 and I am looking at this C epsilon integral, okay, C epsilon 1 integral let us say. Then z is moving on a circular contour. So z will look like 1 plus epsilon 1 e to the power of I theta. Okay. z is 1, this one plus epsilon 1 e to the power of I theta. Okay. So, we have 1 plus z square in the denominator. So, it will be 1 plus z square is 1 plus twice epsilon 1 e to the power of I theta plus epsilon 1 square e to the power of twice I theta. Okay. Now, one thing, this angle here appears to be moving from pi to minus pi. Here the angle will move from twice pi to 0. So, we should be careful to make this 0 to 2 pi, otherwise we may not guess a positive answer over here. We are looking at the magnitude of this integral. So, we should have a positive answer, and so I have set the limits to be 0 to 2 pi. It could be 2 pi to 0 here, it will be minus pi to pi to minus pi over here. So, we should be careful that the integral limits give this side a positive number, that we have to watch. Okay. Now, in the denominator, so let me just say this is for now equal to integral 0 to twice pi magnitude square root of z minus 1 square root of z plus 1, okay, dz. And dz is equal to epsilon 1 I e to the power of I theta d theta, okay, divided by magnitude 2 plus 2 epsilon 1 e to the power of I theta plus epsilon 1 square e to the power of twice I theta magnitude. Okay. Now, in the denominator, so let's write the numerator and denominator separately here. So, square root of z minus 1 looks like square root of 1 plus epsilon 1 e to the power of I theta minus 1, and square root of z plus 1 looks like square root of 1 plus epsilon 1 e to the power of I theta plus 1. Okay. So, this is equal to epsilon 1 to the power half e to the power of I theta by 2, and this is equal to square root of 2 plus epsilon 1 e to the power of I theta. Okay. So, together we have square root of z minus 1 square root of z plus 1 together, and magnitude we will get epsilon to the power half magnitude square root of 2 plus epsilon 1 e to the power of I theta magnitude, okay, and I will take the epsilon half inside. So, I get magnitude square root of twice epsilon 1 plus epsilon 1 square e to the power of I theta. Okay. Now, we have these inequalities in the complex plane with complex variables, which say that the magnitude of z1 plus z2 is greater than or equal to the magnitude of Z1 minus the magnitude of Z2. So, the idea now is that we would strictly like to make this inequality a less than. So, we replace the numerator by something bigger and we replace the denominator by something smaller. Okay. So, using this inequality we say that the denominator, so we have 2 plus 2 epsilon 1 e to the power of I theta plus epsilon 1 square e to the power twice I theta magnitude is greater than or equal to the magnitude of 2 plus epsilon 1 e to the power of I theta close minus epsilon 1 square. Okay. Further, if epsilon 1 square is a small quantity, 2 plus epsilon 1 e to the power I theta is bigger than this, bigger than epsilon 1 square. If I replace this 2 plus epsilon 1 e to the power I theta by one more smaller quantity, then the difference will be further smaller. So, what I say is that magnitude of 2 plus epsilon 1 e to the power of I theta minus epsilon 1 square is greater than or equal to magnitude 2 minus epsilon 1 e to the power of I theta minus minus epsilon 1 square. So, I have replaced the denominator with a smaller expression. Similarly, for the numerator I have twice epsilon 1 plus epsilon 1 square e to the power of I theta magnitude, okay, that is less than or equal to the magnitude of 2 epsilon 1 plus the magnitude of epsilon 1 square e to the power of I theta, okay, which is equal to twice epsilon 1 plus epsilon 1 square. So, here dz now is magnitude epsilon 1 I e to the power of I theta d theta and therefore equal to epsilon 1 d theta. Now, if I write it here, we get that equal to integral 0 to not equal to strictly less than 0 to twice pi root of twice epsilon 1 plus epsilon 1 square epsilon 1 d theta divided by 2 minus epsilon 1 minus epsilon 1 square. You can put magnitude or you cannot put magnitude, does not matter. Okay. This way only d theta is part of the integral, all the epsilons can be taken out. So, we get that this equal to magnitude square root of twice epsilon 1 plus epsilon 1 square by magnitude 2 minus epsilon 1 minus epsilon 1 square into epsilon 1 d theta. And I have not been putting it but actually the limit epsilon 1 tends to 0. And therefore, because there is this epsilon 1 sitting over here, and in the denominator 2 is the biggest term, this goes to 0. The integral goes to 0. So, the magnitude of C epsilon 1 goes to 0. Similarly, the C epsilon 2 also goes to 0. The C epsilon 2 integral also goes to 0. Time has run out, so we will complete the problem in the next lecture. We will look at the other portions of the integral. Okay. Thank you. We close here.